So in the electrostatics, the 5 marks question will be Gauss law and its application. Now let us state the Gauss law first. The total flux phi, we know that the flux is nothing but the number of lines passing through any surface. The total flux phi through any closed surface in free space is equal to 1 by epsilon naught times the charge q enclosed by the surface. That is, if you write the mathematical formula, the flux is 1 by epsilon naught times of q enclosed or q in, or integral over E dot ds is equal to 1 by epsilon naught times of q in. Now to prove this, if you take a sphere of radius r and a small area s, and at the center, suppose if positive q charge is there, then we know that electric field E is equal to q by 4 pi epsilon naught r square at any point on the circumference of the circle. Now if you imagine one aerial element whose vector in the direction outward normal for any area is called area vector. For example, this is a cylinder. This cylinder has a radius, three surfaces. One is this surface, the other one is bottom one, and then curved surface. This, if you want to make this area as area vector, we have to assign a direction for it, and this outward normal is the direction of area vector. So here we imagine one aerial element, and then this is the area vector. Now if you take integral over E dot ds, that can be written as E ds cos theta. Now E is nothing but q by 4 pi epsilon naught r square. So let us replace that. Now we know that ds cos theta by r square is nothing but the solid angle, small solid angle. Now we also know that integral over d omega is always equal to 4 pi. Now if you take this step, I can write it as this step: integral over q by 4 pi epsilon naught ds cos theta by r square can be written as d omega. Now q by 4 pi epsilon naught, as they are constants, it can be taken out. Now integral over d omega can be replaced by 4 pi. So this 4 pi is cancelled with this one. Finally q by epsilon naught. So the total flux E dot ds for a closed integral is always equal to q by epsilon naught, is the mathematical statement of Gauss law. Sometimes a question can be given that a balloon is there and the charge given on the balloon is positive q. Now if the balloon inflated and its radius is doubled, initially suppose if it is r, now it is 2r. Now, what should be the change in the flux? Remember, the flux is nothing but Q by epsilon naught. So, neither Q is changed nor epsilon naught is changed. Therefore, the flux remains unchanged. But electric field at any point on the circumference will be changed because electric field is depending on the radius or the distance. Okay, so that could be one of the conceptual questions. So remember that flux remains same if there is no change in the charge. Now at the same time, the flux, suppose if plus q and minus 2q is here, then what is the total flux means? You have to take the algebraic sum of the charge. So here it is minus q by epsilon naught will be the total flux because charge is additive. Now the general formula is E dot ds is equal to q by epsilon naught. This is one way of writing flux or writing Gauss theorem. The other one is E times area is equal to 1 by epsilon naught times of q. So this is there when if area is already known to us and the electric field direction and area directions are already known to us. Now let us do some of the applications. The very first application is, suppose if a line charge is there, a linear charge q is there. Now somebody is interested to find the electric field at a distance r from this place, from this line. So this P is point of interest. Now how to find the electric field? By using Gauss law. So to find the Gauss law, first of all we have to take the Gaussian surface. Remember, the Gaussian surface must pass through the point of interest. Then second, Gaussian surface, if it is symmetrical, it is very convenient to deal with. So you can find the electric field at this point by using Coulomb's law also. But if you use the Coulomb's law, then we have to resolve the vectors and then it will be very complicated. So when compared to Coulomb's law, Gauss law is very simple. So the simple step is, first of all you have to imagine the Gaussian surface and that should pass through the point of interest, and that Gaussian surface should always be symmetrical. If it is symmetrical, it's very easy to deal with. Now let me take the Gaussian surface here in this case as a cylinder. Okay, now this cylinder is passing through the point of interest. Now here this is the direction of electric field. Now this is having three areas. So one is this circular area at the top and bottom. So this vector direction A2 and this vector is A1, and the curved surface area is in the direction of E. So let me show, if this is the cylinder, this is one surface, this is one surface, this is another surface, and this is the curved surface. For this area, this is the outward normal. For this area, this is the outward normal, and for curved surface, the normal that is coming out is the area vector. Now, according to Gauss law, if you write the statement E times A1 plus E times E dot A2 and E dot A3. So this is the total flux. But total flux is always equal to 1 by epsilon naught times of the charge inside this cylinder. Okay, charge in Gaussian surface. Now here if you closely observe, the electric field vector and A1 vector are perpendicular to each other, and similarly electric field vector and A2 vector are also perpendicular to each other. Therefore their dot product becomes 0. Now the direction of A3 and E are in the same direction, therefore you can write E times area of curved surface is 2 pi r L, where L is the length of the cylinder, is equal to 1 by epsilon naught times of Q in. Now E is equal to Q by 2 pi epsilon naught R L. But we know that Q by L is only lambda, therefore 2 pi epsilon naught R. So final result E is equal to lambda by 2 pi epsilon naught R, which implies E is inversely proportional to R. So with this it's very easy to calculate the electric field at any point by imagining the Gaussian surface. So this is our first application. Now let's do the second application. Suppose a charged sheet is there, then what should be the value of it? What should be the electric field? For example, this is the charge sheet and a plus charge is given. Now at this point somebody is interested to calculate the electric field. Then the Gaussian surface is again a cylinder. Now this cylinder must also cover the point of intersection and it should be pierced through. Now again we have already taken the Gaussian surface. Now we have to decide the directions of electric first area vectors. So area vector here, this direction will be in this one, this will be outward normal is always direction, and then curved surface area A3. Now electric field, suppose if I consider this as the charge, so this as the charge sheet, this charge sheet, if on this charge sheet if electric field is here, this vector will be acting like electric field vector. Now here again we will write the same step, E dot A1 plus E dot A2 plus E dot A3 is equal to the charge within the Gaussian surface by epsilon 0. Now A1 and A2 are equal to pi r square only because it is circular, and then this radius is r. So this will be E times pi r square and this will be E dot pi r square plus, here the dot product becomes 0 Why? Because this is the electric field vector and this is the area vector. The angle is 90 in between those two. Therefore, this dot product will be 0. Now, this will be equal to Q by epsilon naught. Remember, these two are to be added because both are outward flux only. So, when outward flux it is there, so 2E times pi r square is equal to Q by epsilon 0. Now, E is equal to Q by 2 pi r square epsilon 0, and then Q by pi r square is sigma by 2 epsilon naught, where Q by pi r square is sigma, the surface charge density. Okay, so now the interesting part of this result is this. If you observe the final result, what is final result here? E is equal to sigma by 2 epsilon naught. So this result is very interesting because it does not depend on the distance from the sheet to the point of interest. Even if somebody is observing from this point, or somebody is very close to this point, for all the points the electric field remains same as it is independent of the length of the cylinder. So this result is E is equal to sigma by 2 epsilon naught. Now based on this, one more application can be solved, that is suppose if two charge sheets are there. This is one. Remember, this derivation is for infinitely charged sheet. Now this is positive charge and this is negative charge, suppose. Then it divides the space into three regions. So what is the electric field here? What is the electric field here? If the charge density on the first plate is sigma A and second plate is sigma B. To find the electric field in the first region, we imagine a point positive charge or unit positive charge. Because of this positive charge, it is being repelled. So this will be repelled with sigma by 2 epsilon naught. Just now we have derived. Okay. Now because of this negative, it will be attracted. Therefore it is sigma B by 2 epsilon naught. The direction of electric field due to positive plate is in this direction, and due to negative plate it is in the opposite direction. Therefore if you consider that sigma A is greater than sigma B, then net result will be sigma 1 by 2 epsilon naught sigma A minus sigma B. You can discuss a special case here. If sigma A and sigma B are equal, then this factor will be 0. So that is the case in the parallel plate capacitor. In the parallel plate capacitor, the electric field is always restricted to inside only. Outside, if you discuss for this one, because of this positive charge will be repelled, so E due to positive, and because of this it will be attracted, and remember that is independent of the distance. Therefore this again the same result will come here, sigma A minus sigma B by 2 epsilon naught. Now if sigma A is equal to sigma B in a special case, just like in the parallel plate capacitor, then automatically it becomes 0. Now what happens in the second region? So here if you imagine a point unit positive charge, it will be repelled by this one, and it will be attracted by this one. So here the two vectors are in the same direction. So we have to add sigma A plus sigma B by 2 epsilon naught. Suppose if sigma A and sigma B are equal, then that is in the case of parallel plate capacitor, that must be equal to 2 sigma by 2 epsilon 0. Therefore sigma by epsilon 0 is the electric field within the capacitor. Okay. Now suppose if this is positive and this is positive, in that case here both will be in the same direction. So sigma A plus sigma B by 2 epsilon naught, and here this both two will be in the same direction, sigma A plus sigma B by 2 epsilon naught, but in between because suppose if it is positive, then it will be repelled. It is also positive, it will be repelled in the opposite direction. Therefore sigma A minus sigma B by 2 epsilon naught. And if you take sigma A is equal to sigma B, inside the two plates, if they are of same nature, inside the plates it becomes 0, outside only electric field exists. Okay, now let's discuss the case for spherical shell or hollow sphere. So suppose if you give the charge to the hollow sphere, the charge will come always outside. So Q charge is given, and this R is the radius of the spherical sphere. Now spherical shell, now or hollow sphere. Now we have to find out the electric field at different positions. So first let's talk about inside. So inside at small r. So we know that wherever our point of interest is there, we have to imagine a Gaussian surface there. So we have imagined one Gaussian sphere. Now what is, according to Gauss law, integral over E dot ds is always equal to 1 by epsilon naught times of Q in. This we are calculating when R is less than the radius. Now what is inside charge? Whatever the charge is given to the hollow sphere, it always comes on to the surface of it. Therefore Q in is 0. Q in this case it is 0. Therefore electric field E dot A, which is equal to 0, or you can say E is equal to 0. So the electric field inside hollow sphere is always 0. Now what happens on the surface of it? So now again you have to take the Gaussian surface. So in this second case,